All right, welcome. Today we are going to tackle a topic that can make a lot of people just a little bit nervous: graphing exponential functions. But you know what? We're going to forget all that stress and think about it in a totally different way. We're not just solving a math problem here. We are decoding a set of instructions, a blueprint for a really cool-looking curve.
So take a look at this. I mean, at first glance, it looks pretty complicated, right? It's just a jumble of fractions, exponents, negative signs. It's really easy to look at that and feel a little overwhelmed.
But what if I told you that every single number and every single symbol in that equation is just one simple step-by-step instruction? We're going to treat this whole function like it's a blueprint, and I promise by the end of this, you'll be able to read it like an absolute pro.
Okay, so let's dive right in. We have to start with the most basic version, the one we're going to call our original blueprint. Every single complex exponential function, no matter how wild it looks, starts with this simple foundation: f of x equals b to the power of x.
You see, every exponential graph starts out as one of two fundamental shapes. If that base number, b, is bigger than 1, you get what we call exponential growth. It looks kind of like a rocket taking off. But if b is a fraction, something between 0 and 1, you get exponential decay. Think of it like a smooth landing. At its heart, it's either growing or it's decaying. That's it.
Now, what's really cool is that this original blueprint has fixed rules. Think of them like factory settings. The domain just means it goes on forever to the left and to the right. The range means it only exists above the x-axis. And get this, it will always cross the y-axis right at the point 0, 1. And it gets super close to the x-axis. That's the line y equals 0, but it will never, ever touch it. That line is its horizontal asymptote, like an invisible floor.
So let's get to our first set of instructions and see how we build on this. We're going to take our original blueprint and just start shifting it around on the page.
The first instruction is honestly the easiest one. If you just add or subtract a number after the main part, you literally just lift the entire graph up or push it straight down. A +3 moves it up 3. A -5 moves it down 5. It's as simple as that.
And here's the crucial part. When you shift that graph up or down, that invisible floor, the horizontal asymptote, it moves right along with it. So if you shift the whole graph up by 1, well, the new floor is now at y equals 1. The graph will get close to it, but it's never going to cross it.
Okay, now for the horizontal shift. This happens when you add or subtract a number right up there next to the x in the exponent. This instruction slides the entire blueprint left to right. But there's a little catch here. Yeah, this is the one weird rule that tries to trip everybody up, so listen close. In the exponent, the direction is the opposite of what the sign tells you. So x minus 3 doesn't go left, it actually moves the graph to the right. And x plus 3 moves it to the left. Just gotta remember, inside that little exponent world, things are kinda backwards. All right, so we can move our blueprint around. Now let's see how we can stretch it or kinda squish it using multiplication. This is what changes how steep that curve gets. So this instruction is controlled by a number multiplied out in front of the whole thing. We call it a. If a is a number bigger than 1, like 3, it's a vertical stretch. It basically yanks the graph upwards, making it grow way faster. If a is a little fraction, like 1/3, it's a vertical compression. It squishes the graph down, making it much flatter.
And now for the final modification in our toolkit, how to flip the entire design. We can either flip it completely upside down, or we can create a perfect mirror image of it. And this shows the two ways we can reflect our blueprint. A negative sign way out in front of everything flips the graph over the x-axis, turning our rocket launch into a nosedive. A negative sign right next to the x up in the exponent flips it over the y-axis, creating a perfect mirror copy.
Okay, we have all our tools. We have shifts, we have stretches, and we have flips. So let's go back to that intimidating equation from the beginning and read it like the simple set of instructions it really is.
And here it is, your master key. This little table summarizes every single instruction we just learned. Seriously, feel free to pause right here if you need to. This is everything you need to decode pretty much any exponential function they throw at you.
All right, here it is again, our big challenge. But this time, it doesn't look so scary, does it? We can actually see the instructions hidden in there. Let's break it down piece by piece. So, here's the recipe. Step 1. We look at the base. It's 1/2. That means our original blueprint is a decay curve, gliding downwards. Step 2. The shifts. The x minus 3 up top tells us to shift right 3 units, and that +1 at the very end lifts the whole thing up 1 unit. And finally, step 3. The 2 out front tells us to stretch it vertically, and that lonely little negative sign, well, that flips the entire graph upside down.
And there's our final result. We started with a simple decay curve, we slid it right 3 and up 1, which, remember, also moved our invisible floor up to y equals 1. Then we stretched it out and flipped it upside down. From a messy-looking equation, we got a perfectly predictable picture. Pretty cool, right?
And this isn't just about making shapes on a page for a math class. It's so much more. Seeing these pictures gives us this incredible insight. It lets us visualize things like how money grows in an investment, or how a population might change over time. It gives us a way to actually see the future that the numbers are trying to predict.
So now you have the key. You can read the blueprint. You can look at a really complex-looking exponential equation and actually see the story that it's telling. So the question I leave you with is, what future could you predict? What story could you uncover?